This is lesson 10 of the quantum mechanics, a mini lecture series titled Einstein's Work Part 1. So in 1905, a young German physicist named Albert Einstein, only 26 years of age, wrote a series of papers, one of which was based on the photoelectric effect. Photoelectric effect, okay? Albert Einstein, world-renowned. And here's what he did. He actually used Wien's formula for black body radiation. That was his starting point. And his method so he wanted to actually fix the issue. So he wanted to explain the photoelectric effect, what was happening, because classical physics was obviously failing. He used what's called a phenomenological approach. Okay, which means an experimentally based approach. He was using the experimental results rather than just using a theoretical one. Okay, and he also used some thermodynamics, okay, some heat theory. And he arrived at the conclusion that radiation, the light, is behaving as though it consists of energy quanta, of little packets of energy, as Max Planck came up with. Energy quanta. Okay, quanta is plural for quantum. Okay, little packets of energy. So that's what light. That was the picture that Einstein had in his head in terms of light. And he actually believed that light, all forms of light, radio waves, microwaves, they were all quantized. They all consisted of these chunks. Okay, E equals NHF. So he believed that this applied to all forms of light. Okay, and you couldn't have half an HF. You can only have whole number packets of energy. HF, 2HF, 3HF. N is an integer. And so Einstein therefore believed that all light and electromagnetic radiation travels in bundles of energy equal to this, NHF. And this was Einstein's picture of the photoelectric effect. Suppose you've got a metal surface here. Metal surface. You've got electrons sitting here. Okay, so light comes in, energy, let's call it HF for now, of a very specific frequency, and out comes some electrons with some kinetic energy, Ka. And there was a one-to-one correspondence with the energies in that one photon coming in would release one electron. And there was also something characteristic of the metal, okay, because this only applied to metals, called the work function, W. It's a number. And so each electron also needed to perform an extra amount of work, okay? I'm going to call it W. Okay, work function, this is a number which basically dictates the ease of an electron escaping, okay? And so the kinetic energy of each electron now, it's basically equal to the energy of light coming in minus some work function, okay? That's energy coming in. That's what's needed to leave out of the middle. And from before, if you remember, the kinetic energy is equal to Q V sub naught from a previous video. And using this, you can work out things like retarding voltage, etc., etc. Okay. And a bright light beam would indicate lots of photons, right, according to this picture. And this was, if you remember, the retarding voltage indicates, so it basically tells you what you need to get no photoelectrons coming out. So you can basically stop photoelectrons, the emission of electrons coming out of the middle, by applying some voltage, as I mentioned before. But this relation here, this is what Einstein believed. Not only was the kinetic energy of the electrons equal to HF, energy of the light quantum, I should mention, but also you need to subtract this work function. The electrons need to do some work. Okay? Work in physics means some extra effort, some work, some force, some action. And I'll talk more about this relation here and why it's important in the next video.